How you doing? I'm Mr. Rose, and today we're back in the dungeon to learn about the rotation of rigid bodies. So to this point in our journey, we've talked a lot about translational motion. Now, translational motion obviously is anything that goes back and forth in a straight line, but also follows this nice parabolic path that we've talked about for a long time. Well, now if you picture an object that is a rigid body, and a rigid body is, as we should know, any object that is solid, that moves together as one piece, that applying forces to it doesn't change the shape, doesn't deform that object in any way, shape, or form. If I take that object and I throw it across some path, we would see that it travels in that parabolic path, but it is a little bit more complicated than that. If you look at my three pictures here, you see that there's a slight rotation of that object. Well, we know the center of mass is going to carry on that parabolic path, but we're now going to examine that rotation of our object. To do so, we're going to start with a couple of limiting principles. One of those limiting principles are we have a fixed axis of rotation. That fixed axis of rotation means that our axis is only going to stay in one place, rotate around that object. Again, we're only talking about rigid bodies as well. These two things do give us a little bit of a limitation. Those limitations are we can't talk about things like the sun. The sun, as you know, is a giant ball of gas, not a rigid body. We also can't talk about moving objects at a time or moving rotational objects, like a thrown baseball or a bowling ball rolling down the alley. So what that means is we are right now talking about some kind of object like I have here of any orientation, rotating about that axis and that central point. This dotted line I'm saying is our rotation, and here is our axis of rotation. So this object is going to start rotating around this one point. So moving forward, I have two pictures here that look very similar. So I'm going to need you to put your imagination hat on. This picture is a three-dimensional object, let's say like a basketball. And that basketball is going to start to rotate around this axis that I have labeled the z-axis. So it's just going to rotate and rotate and rotate and rotate around. In order to measure things from this rotation, we need to make this reference line that I have drawn in pink. Now this reference line is perpendicular to our axis of rotation. And to take measurements along that reference line, we're going to cut that basketball into a cross-sectional area. So now I'm looking straight down that axis of rotation, so now I'm looking straight down at the y and the x-axis, and I can start to see that reference line starting to move. Well, I have two things labeled here in that as that reference line moves across. I have a theta and an s. Now, theta is that angular displacement that we can actually measure the reference line moving from x as we rotate around that object around our z-axis. Now, this point that I have on my reference line is going to start to carve out a path. That carved out path we have labeled as S. So what we can start to see here is that as this rotates around, my angular displacement, theta, is going to get bigger and bigger and bigger, and I'm going to carve out that distance S around my circle. This is by definition a radian measurement. We have here that theta, as theta gets bigger, wherever S is, S and R are related to each other. So this is my angular displacement in radian form. My arc length S is bigger if R is bigger. My arc length S is smaller if R gets smaller. That seems to make sense. Things that we should remember about radians, we know that a circle obviously has 360 degrees, so there are 2 pi radians in every 360 degrees. I noticed something wrong in our notes here. This should say 1 radian is equal to 57.3 degrees, which is equal to 0.159 revolutions. Now, radians are a dimensionless unit because a radian is just a ratio. So when we do things, when we're finding out our theta or that radian angle, those are just pure numbers. So now we start to see that we have this new language being approached. We have our translational motion, which has always been x with response to, in regard to t, displacement as time goes on. Now we have this rotational motion. Theta changes with respect to time. One last thing, as you can see I have written down, radians don't reset like degrees. So the number of revolutions that happen, my radians just keep adding up. So 2 revolutions, for example, are 4 pi radians. To move on, And to develop this brand new language, we need to be able to describe these angular displacements in different terms. So here we know we just spoke about that angle theta. Well, a change in my angular displacement is obviously theta 2 minus theta 1. Again, that's regard with that reference line that I had drawn earlier. We also know that they can be positive or negative. Well, how do we know if it's positive or negative? A good way to remember this is just remember the phrase clocks run negative. What that means is anything that is rotating in a clockwise fashion is going to have a negative magnitude. Anything that is rotating in a counterclockwise rotation will have a positive answer. So if we have some displacement, that must mean if I have a displacement with respect to time, I can figure out what an average velocity is. Well, my average velocity or angular velocity is going to be brought to us by, that's not a W, that's an omega. My average velocity or my average rotational or angular velocity is my change in theta with respect to time. What if I don't want an average? What if I want an instantaneous velocity? Well, then we can introduce some calculus and we can say the limit as t approaches 0 is just d theta dt. What is that? Change in angular displacement at some specific unit of time. Likewise, just like we did with translational motion, we can go one step further. We can say, well, what if I need an angular acceleration, or as we know, we'll come to know it, a alpha? Well, just like we have an average velocity, we can have an average acceleration of our change in omega with respect to time, or we can take the limit as t approaches 0, and we get a dw dt at some instant time. Now, I know what you're thinking to yourself. You're thinking, are these values all vectors? And your first thought is, yes, they probably are. But in order to be a vector, we need to have a magnitude and a direction, which we know. We also know that we need to hold to vector addition. So if you look at my diagram here, what I have drawn here are just two simple objects. Let's say a box of cereal. If I start with my box of cereal one way, and then I rotate it, say, about an axis this direction, you can now see that I like to eat Wheaties. If I turn that again, I'm going to rotate this way. All of a sudden, we're looking at the bottom of the box of cereal. We're going to do the same exact thing, except now I'm going to change the order, in which I'm going to rotate first about this vertical axis like so. Now I'm going to rotate the same direction I did last time about this horizontal axis, and all of a sudden we're looking at a different side of the box. That seems to be a little bit confusing, but what that means is I cannot treat this angular position, theta, as a vector unless it is very, very, very small. What does that mean for us? That means we need to introduce the right-hand rule. What the right-hand rule does is that gives us the direction of omega with respect to what's happening. You take your right hand, you put your fingers around the axis of rotation in the direction it's rotating. So in this picture here, my axis of rotation, my fingers are rotating that way. My thumb is pointing the direction of that angular velocity omega. Lastly, we have a complete new language. Everything over here is our translational values, and we've come to use these a lot with all of our missing terms. For every translational value, there is a rotational or an angular equivalent. We're missing a velocity, we're missing an omega. If I'm looking for an acceleration, that means I'm looking for an alpha, as opposed to earlier when I was looking for an acceleration. All of our physics, however, is going to be the same thing. Well, what if you were an inquisitive child when you were small and you were thinking to yourself, if I'm rotating around something like a merry-go-round, is my linear speed constant? Because I didn't know all of these things when I was a child. I also started to think, well, what if, and all of us did this, what if I was as far away from the center of that merry-go-round as possible? I could go fast enough that I could hold on like in a cartoon and flap in the wind. Well, to do that, we could do one of two things. First, we can think of it as a simple conceptual problem where we know linear speed is distance over time. Well, if I'm going around that merry-go-round at a constant angular speed, but depending on how far away I am, if I have a bigger radius, r, that must mean I'm covering a bigger distance, as we talked about earlier, s. So my tangential velocity, v, or my linear speed, depends on how fast that's rotating around in a circle, and my radius, which means if I'm further away from the radius, my tangential velocity is bigger. Again, remember that S is equal to R times theta. And now if I was a real smart kid and I didn't want to do it conceptually, I could do it with just some straight calculus. As that arc length changes with respect to time, I'm going to get a change in angular displacement. We have d theta dt is just my angular velocity, and we can see velocity is r times omega, velocity is r times omega. Well, again, what if you weren't the kid that was on the merry-go-round? What if you were the kid that made the merry-go-round go faster and faster and faster? Well, then we're going to talk about acceleration. Now, here's the tricky thing. If I'm talking about an acceleration with respect to time and that angular acceleration, there are actually two components to that. We can say my change in velocity with respect to time I know is just an acceleration, but then when I look over here, my change in omega with respect to my change in omega with respect to time as I go further out or smaller in, I get what is a tangential acceleration. At is equal to alpha, that's my rotational acceleration times the radius. But we have already learned, and now this might be where you came up short as a very young child. We learned recently that anything that's going around in a circle has this radial component of acceleration. There has to be a force going towards the center of the circle, which means there's a radial component of that acceleration. We already know that that acceleration is v squared over r, and we just figured out that v could be r times omega, which means I now have a radial component of acceleration that points towards the center of that merry-go-round of omega squared times r. All of this is going to help us with our journey going forward. Last thing to remember is that all this does happen with respect to time. Now, time, we're talking about revolutions of any type of circle, since we're talking about rotation. We know that one revolution is 2 pi r divided by the velocity, and we can do simple substitution to find out that the period of rotation is also 2 pi over omega. Thank you for your time. Sorry this was a little long. Please comment, like, subscribe, anything you want to do. Maybe we can get some funding to get out of the dungeon. Speak to you soon.